Okay. Yeah. Cool then. So shall we begin? I hope I'm audible clearly. So if I'm audible clearly and if the shade screen is visible clearly, click on yes. Okay. If I'm audible clearly, if the shade screen is visible clearly, please click on yes. So we'll move ahead with the concepts. Okay, not much today to learn, only two topics, but they're important. Okay, well, because these concepts keep appearing in the exam, so we'll have to understand them in much more detail. We'll do it. Okay, yeah. Okay then. So we are supposed to start now, right? Okay, we'll begin very quickly, and we'll try to understand as much as possible from today's class. Okay, yeah. So till now we have learned many things in wave optics, right? Like Young's double slit experiment, diffraction. We saw a few examples also, right? We saw what is a black fringe, dark fringe, bright fringe. We have seen many of the things, and now we are going to see a new process in physics called as polarization, right? So polar, you might know what is a polar, right? So polar means which has two ends. For example, like Earth has a north pole and a south pole, and even a magnet has a north pole and a south pole. So you know what a polar is. Polar is nothing but which have poles, right? Yeah. So remember that word. It's a keyword to understand this concept. Okay. So before going into the physics concept, let me tell you where do we use polarizer or polarization. Okay. So for example, while cricketers are playing in the ground, it will be very bright day, right? So then when the ball goes very high, the fielders cannot catch the ball because the sunlight will blind their eye, right? It will block the visibility of the ball. So what they do, they use sunglass, right? What does sunglass do? It will reduce the intensity of sunlight, reduce the intensity, right? You can see the ball. I mean, you can stare into the sun directly without you getting hurt your eyes, right? Or similarly, if you're trying to watch a solar eclipse, right? You can't watch a solar eclipse in naked eye because again, harmful radiation will be emitting from Earth. It will be very harmful for your eye. But you know, if you take a solar glass, or as there are specially built glasses to watch the solar eclipse, or if you take an X-ray also, you can watch them. So what does it do? Even though the X-ray sheet or the solar glasses, right, they also do the same thing, which is reducing the intensity. And whenever such radiations are getting reduced, and that process is called as polarization. Okay, so polarization is a process in which we are going to reduce the intensity of incoming radiation. Okay, for example, initially I have very much radiation, I can't watch that bright source, but I use something called as a polarizer. Okay, so by which I can reduce the intensity of the incoming light, and everything will be possible and very clear now. Okay, so for example, you can see in the diagram I have shown in the diagram here. See, there is lots of wave coming. See, there is one orange wave, there is one yellow wave, and there is one sky blue wave. So there are three waves, a lot of energy wave. They're coming from a source. They're coming from a source. And what you do is, I'll take an instrument called polarizer or polarizing filter. It's simply called as polarizer. When this high intensity light passes through this polarizer, what does this polarizer do? It will allow only certain radiation to come inside. Other radiations will be blocked. For example, you can see here, only the yellow radiation is getting passed through this, right? You can notice there are lines like this here. Only which radiations which are actually parallel to this line will come out. Other light, like the blue light or the orange light, are getting blocked. So there was three light waves here. Initially, there are three light waves here, right? Light waves, and now there is only one light wave, one light wave. So what's happening here? If you can notice in this example particularly, initially very bright wave, which are very high energy, is reduced and it has become very low bright because only one light is passing through this, right? So this is called polarization, and this is a polarizer. A polarizer is an instrument which is going to reduce the intensity of light. Okay, yeah. And if you notice very clearly, let us name some of this and we'll try to understand. Okay, so this here, it's called an unpolarized light. So unpolarized light is something which has a lot of intensity, and there is something called as polarized light. Polarized is very less intensity when compared to the unpolarized light. Okay, and this instrument which is reducing the light or polarizing the light is called as a polarizer or a polarizing filter. Sometimes it is also called as an analyzer. Okay, there are many names, but all of them are same. There is no difference. Okay, and one more thing which is important is why is it called unpolarized and why is it called polarized? Okay, if you notice here, this also have only upper value like a north pole and a south pole, a north pole and a south pole. So this is like a polarized value, right? It has something similar to only two values in a particular plane. But if you notice here, there are many planes here. There is one plane on for yellow, for one plane for orange, one plane for blue. So there are many poles here. There are many lines. There are many axes. So this is called as unpolarized light. But this, whereas only one plane, right? Only one wave it has, so it is called as a polarized light. Okay, I hope I'm clear, right? Okay, so this is what's basically happening in the whole concept. So we'll try to understand some mathematical formulation. We'll try to understand a better concept in a much more detailed way. Okay, how to represent this diagrammatically, because all the time whenever they ask an exam, we can't draw such a beautiful diagrams, right? So we have to draw them in a scalar way, in a very block diagram way. So we will try to understand and write them in very simple way. Okay, so very simple. What is polarization? So polarization is a process in which the unpolarized light of high intensity is passed through a polarizer and it becomes a polarized light of low intensity. Yes. Okay, very simple. Okay, am I clear, guys? Zoom guys, YouTube guys, hello, hi. So am I clear with this concept? Are you clear with the idea? So if you're clear with the idea, we can build on to the concepts. Okay, we'll try to understand it a much more better way. Okay, so with that introduction, okay, let us go ahead. And today, introduction ka polarization ho gaya. So we'll see there are three ways of polarizing a light or a radiation. So there are polarization by selective absorption. By absorption, we can polarize. By reflection, we can polarize. By scattering, we can polarize. So there are three ways of polarization: one, two, and three. So we are going to see what are these three ways, and lastly, we'll see what is resolution of an image. Okay, resolution of a image. For example, you're very familiar. Okay, when you're watching a video or a movie, you're very familiar with this word 360 pixel, 720 pixel, or 1080 pixel, right? So these are nothing but resolution of a video. Similarly, we're going to understand what is the resolution of an image. Okay, so we'll try to understand what is resolution, and by this four concepts, if whenever complete this, the chapter will be done. Okay, so not much remaining, very few things are remaining, but let us try to use time and complete it very quickly. Okay, yeah. So the first thing which I'm going to say is, we know that how do we represent a light? We represent a light by oscillating electric field and magnetic field perpendicular to each other. So if you notice, if I say that this red light is electric field, okay, which is oscillating in y-axis, right? Above, above and below. Right? It's rotating above and below. And if you notice, there is one more field here, which is the magnetic field, which is oscillating in this direction, magnetic field. So E and B are always perpendicular to each other. Electric field and magnetic field are always perpendicular to each other, and they are wave. So you can notice here, right? This electric field is increasing, decreasing, decreasing, increasing, right? So this is oscillating electric field. This is oscillating magnetic field. And we had a separate chapter called EM waves, in which we have learned as much as possible, right? Okay, so yeah, we are going to do the same thing here also, but we have to be very careful, which is we are not going to consider magnetic field for this concept. No, we are not going to consider magnetic field, because the polarizer which I'm going to use here, this only interacts with electric field. This only interact with electric field. It doesn't interact with not no magnetic interaction. No magnetic interaction, because if you know, almost most of the objects in the universe are non-magnetic. For example, if I take a pen, in a pen there is electron, there is proton, there are charges. But is there any magnetic properties for a pen? No. If you take your phone, there are charges in your phone also. No, not in the charger itself, like on the screen, it's a capacitor. All of the objects which you see in the universe carries a charge, but not all of them carries a magnetic field. So we'll not consider magnetic field because it doesn't interact very much. We're only considering electric field. Okay, so all of this here, what I've written, this is electric field, yellow electric field, this is sky blue electric field, this is orange color electric field. They're all electric fields. Okay, I've neglected magnetic field completely. Magnetic field ko pura neglect kiya. Okay, so just only will consider electric field. Okay. So, and we also know that light behaves like a transverse wave. That means it goes up, it comes down, right? It's not a longitudinal wave, but rather than it's a transverse wave. So we know that also already, and it is always alternating. As I already told you, red is electric field, blue is magnetic field, and we are going to consider only electric field. Okay, no magnetic interaction are considered for polarization. For polarization, we'll not consider this. Okay, because they don't interact much with objects. Okay, so and initially I told you that in the polarizer we are going to convert unpolarized light into a polarized light. So what is the unpolarized light? It's a kind of light in which there is electric fields E are vibrating in all the planes. Or for example, here you can notice, right? So here electric field is vibrating in all the planes. It is vibrating in the yellow plane, it's vibrating in the sky blue plane, it's vibrating in the orange plane. Electric field is oscillating in all 360-degree. There are many axes of electric field. There are many ways it's oscillating in as much as directions possible. Okay, so that kind of unpolarized, that kind of light is called as unpolarized light. Okay, and this is how we denote. So this is oscillation of one color, blue color here, blue light wave was oscillating there, here red wave is oscillating in this direction, and green wave is oscillating in this direction, and yellow wave, one more different wave, is oscillating in this direction. So here electric field is oscillating in all the direction. So this kind of light, where do we get this kind of light? This kind of light is uh, emitted by sun. Okay, so like sun, candle, light bulb, all of the sources what we get light are unpolarized. So basically sun gives out electric field oscillation in all the direction. Candle light also gives out oscillation in all the direction, or a bulb gives out oscillation in all the direction. And this is how we represent an unpolarized light. So oscillation of electric field, this is E1, this is E2, this is E3, this is E4. There are many electric field oscillation in many axes. Okay, and okay, so again, this is very much very tough to draw, or simply we'll draw unpolarized light in this way. Okay, one axis is here and one more dot here. So this means an unpolarized light. So this is a representation of an unpolarized light. So this is how we represent it. Okay, so this means that there is one field oscillating up and down, and there is one field oscillating towards right and left. Okay, so this is how we denote an unpolarized light in a block diagram. Okay, so this is very easy to draw, right? This is very tough to draw. So we'll not use this, but we'll use this. Okay. Okay, so as I already told you, light well emitted by sun, candle, natural lamp, they're all unpolarized light. Okay, so let me give you much more idea. How does a polarizer work? Okay, so imagine guys, you have a wave. Okay, you have a wire, you have a rope. Okay, and you're taking that rope and you're oscillating. You are taking your hand, holding this rope, and you are moving it up and down. Okay, you're moving this rope up and down. What will happen? The waves are generated, and these waves are traveling. Okay, and in between, have kept a plate here, and I've cut a small part in the plate from north to south. I've made a very small cut from north to south, and when I'm oscillating the wave north to south or up and down, the wave will pass, right? Because it's not a problem. That is how the wave is getting oscillated. It will pass through this and it will come outside, right? I can see the oscillation here also, not a problem. But see the same thing. Okay, I have a slit here. I've tied the rope to one end. I'm holding the rope here. Okay, I'm disturbing it up and down, and it'll move if the slit is also up and down. Okay, but imagine a situation. Okay, imagine a situation in which I rotate this plane. What will happen now? It will be completely blocked, right? Am I right? Because see, the wave is oscillating up and down. The wave is oscillating up and down, but this gap here, this slit is from east to west, sideways. Right now, the wave cannot pass because it is trying to go up, but there is no gap for the wave to go up, so it's completely blocked now. Okay, now it is passing, right? But now it is blocked, and this is what happens exactly in the polarizer. Okay, only few light waves will pass through this particular object, and other light waves will be blocked. Other light waves will be blocked. Okay, cool, right? Did you get this idea? Because this idea we're going to use and understand. Am I clear, guys? YouTube guys, you can comment. Okay, if you understood or if you want some more clarification, you can. Zoom guys, am I clear? Okay, cool, cool. Yeah, sure, sure. Okay, Namrata, cool. Not a problem. Yeah. Okay, very simple, right? Okay. So remember this idea. Whenever some objects are oscillating in the same plane as the slits are located, they pass through it. Otherwise, they'll be blocked. Okay, cool, right? Okay. So okay. So what is a polarization? Or let me explain you the process in detail. It's a process in which a transverse wave, which was oscillating in many directions, is now restricted to only one plane. it will oscillate only in one plane, because as you saw in the initial diagram, there was lots of wave oscillating in this direction, in this direction. But when I pass through that through a polarizer, it's oscillating only in one direction. Okay, so this is what's happening. Only one wave is moving here, only in one plane. Right? There is only one plane, one axis. So that is what we call a polarizer or a polarization. It's a process of converting unpolarized to a polarized light, which oscillates only in one plane. Okay, and how do we denote this polarized light? What do we do is, if you remember, this was an unpolarized light. Unpolarized light had up and down oscillation as well as dots in between, as well as dots in between. So what does this indicate? This indicates unpolarized light. Okay, but how do we denote a polarized light? What we do is we separate the dots from the line. So you see, I remove the dots. There is only oscillation in one plane. This means electric field is oscillating only in one plane in this direction. So this is a polarized light. Or also we can separate the blue lines from the red lines. Okay, so this means that now the electric field is oscillating only sideways. Okay, in this plane. It's oscillating only in this plane. So these two are the representation of polarized light. So this is a polarized light. Okay, and this is also a polarized light. You can write in any way, it's completely fine. Okay, it's a completely fine diagrams, and this is an unpolarized light wave. This is an unpolarized light wave. Okay, cool, right? Yeah, and we have different names also. This kind of polarization is called as plane polarization, and this kind of polarization is called as line polarization. But they're just fancy names given for us for our better understanding. But both of them are fine, not a problem. Okay, if you can see the plane of the wave, okay, then you can call this as plane polarized wave. If you can only see the line of the polarized wave, we can call it as a line polarized wave. Am I clear, guys? I hope I'm clear. Okay. So are given the definitions. Okay, so it's not necessary that you have to remember the definition or you have to buy the definition. If you understand the definition in your own way, you can write them without any problem. Cool, right? Yeah. So am I clear, guys? So am I clear with this concept? Okay. So how do we denote polarized light wave? And if you have understood what's a polarizer light wave, you can click on yes. Come on, Zoom guys. Am I clear? Any doubts? So, or shall I move ahead? Okay. So let me give you one more diagram for better understanding. Okay. So notice here. So there is one polarizer here. There is one polarizer here. What's happening? You can see that many light waves which are unpolarized. These are all unpolarized light oscillating in any direction as much as possible, and they are entering an object called a polarizer. Right? When they enter this polarizer, what is about to happen? This polarizer will allow light only in one plane. See, it's allowing light only in one direction. Only in one plane it's oscillating. This is a plane it is oscillating, right? Yeah, see here, if you notice, there are lots of high intense waves, but here there's only one wave. So it will be having low intensity, this will be having high intensity. And this is called a polarizer. Okay, this is called a polarizer. And what is this polarizer and how can it block the light waves? Is very simple. Okay, a naturally polarizer is nothing but a crystal. In chemistry, I learned about crystals, right? What are crystals? Crystals are something. So let me draw a crystal like this. Okay, in this crystal, there will be molecules, right? There will be molecules. So these molecules are arranged in this. I'm just giving a crude example. Okay, so in this crystal, molecules are arranged in this particular way. Okay, so what's going to happen now is when I put the light, when I pass a torch through this particular pass a torch light through this particular polarizer, what's going to happen? Imagine a light wave which is coming in this direction. If a light wave is entering in this direction, what will happen? If you notice very carefully, this light is getting blocked here. This block is blocking the light here. Again, the light is getting blocked by this block. This crystal is again blocking the light. So light which are passing in this particular axis will be blocked. They can't pass. Okay, but notice a light wave which is passing in this axis. Okay, see, if a light is passing through this axis, you can notice that it will pass through this axis, aram se, right, without any problem, because the crystal structure is well defined. Always in all the crystal, the arrangement will be very fine, very clear. So this will again pass through it, right? It will pass through it. So this is how a polarizer will actually work. Okay, it's nothing. Polarizer is nothing but a. Sorry, you don't want me to write in black? Rajama, can you be more specific? Okay. So what's going to happen is block. Okay, so what's going to happen is when these crystals are arrangement in such a way that these crystals are going to block some of the axes, some of the light in a particular axis. Okay, cool, cool, yeah. And the rest of the light will be passing through without any problem. Okay, it will passing through the problem. Okay, cool, right? So if you notice here, the same thing is happening here. This polarizer has is or it is passing the light only in this axis, right? See the light waves which are coming in this direction, they'll pass through this axis like the slit, as I already told you in the last diagram. They pass through very simply, very without any problem, like this, like the wave pass through a slit, and they go away. Rest of them which are oscillating in other direction are completely blocked. Okay, and this axis in which the light will go from this end to that end is called as vertical polarizer or a polarizing axis. Okay, this axis is called as polarizing axis. The axis from which a crystal is passing a light is called as polarizing axis. Okay, and you can notice here. So this is the block diagram. See here, the light was oscillating in many ways. It was oscillating in all the direction, up, down, sideways. But here, the light is oscillating only from up and down. Okay, so this is a polarized light. Am I clear, guys? Cool, right? Yeah. So and see this oscillation of final wave is happening only up and down. So this is called as vertically polarized light. Or if the same thing happens sideways, for example, notice here I'm taking the same unpolarized light and I'm rotating this polarizer by 90 degree. When I rotate this polarizer by 90 degree, okay, yeah. So what's going to happen? This polarizer is passing through this 90 degree, and now the axis also shifted. The axis also shifted, right? Because the the slit was only possible to allow in this particular axis. Now, as I rotate the 90 degree, the axis also rotate by 90 degree, and only waves which are at this particular 90 degree are passing outside. Other light waves are completely blocked now. Okay, the axis in which the light passes out of a polarizer is called as a polarizing axis. For example, see in the first case, here in the first case, the polarizing axis was north to south. Okay, this was a polarizing axis, the axis in which the light is passing through a polarizer. Okay, and now the light is passing through this axis. Very simple. Now, if I rotate the polarizer by 90 degree, the axis also will rotate by 90 degree, and now blue light is blocked. But if you notice, it is in the same plane as that of a red light, and red light is passing through this polarizer because the polarizing axis is now in 90 degree to the initial direction. Cool, right? And when up and down waves are coming, we call it as vertically polarized light. When side waves are coming, we call it as horizontally polarized light. Okay. Am I clear now? Am I clear about what is polarizing axis? What is a polarizer? What is a polarized light? What is an unpolarized light? Hope I'm clear. Okay. Cool, right? Yeah. Okay. Yes. Okay. Cool. And this one mathematical formulation, okay, for which we have to understand if this has some intensity I, what will be the intensity when it passes the polarizer? It will definitely to be low intensity, but we need to calculate, and there is a mathematical formula also, and we'll try to understand. Okay. Cool. And there are three ways basically. One is by selective absorption, one is by reflection, other is by scattering. There are three different ways in which you can get a polarized light. One is by selective absorption, another by reflection, another is by scattering. Okay. So selective, this is what absorption. Okay. This is an example for absorption. See, this polarizer is absorbing all the other lights except the light which is in the polarizing axis. It's absorbing, this crystal is absorbing all the different light, right? So that is already, I already taught you about one method. I'll tell you much more in detail. Okay, and we'll see what are the other two methods also. So the first method, what is polarization by selective absorption? Okay, so in this method we're going to use a material called polaroid or a polarizer. Okay, for example, sunglass, or if I notice in car, they'll for windows they'll put a gray color sheet, plastic sheet, so that it will not be so much bright when you're driving the car. Okay, so even that is a polarizer or a polaroid. Okay, or a regular crystal which you use in chemistry. Most of these are crystals. Okay, silicon crystal, or it can be any crystals what I learned in from chemistry, and they are and will act as polarizers. Okay, and you might have already understood few things about these polarizers. Okay, they transmit some waves. Okay, they transmit which are exactly in the same plane of a polarizing axis or optical axis. Polarizing axis is also called as optical axis. If a light wave is exactly in the direction of the polarizing axis, it will pass it. The crystal or the Polaroid will send the light away. It will send the light away, right? But for example, imagine if you have a different situation in which the polarizing axis and the light waves are perpendicular to each other. Like if they're perpendicular to each other, it will absorb all the other light waves. For example, imagine there is one polarizing axis in this direction and the light wave is coming in this direction. Okay, now the light wave, we cannot pass through this polarizing axis and you will not get any wave at all. It will be completely blocked. So what happens to this wave? This wave is getting absorbed by this crystal. Okay, this is getting absorbed by the crystal. Very simple, right? Okay. And always remember, this is the most important point for problem solving. Whenever for the first time, if you polarize an unpolarized light, for example, if the input is unpolarized, if the input is unpolarized light, and if the output is polarized light for the first time, okay, if this has an intensity of I naught, the polarized light will have an intensity of I naught by 2. For the first time, always whenever some light is getting and some unpolarized light is getting polarized, always the intensity will be half of it. Always remember this. Okay, will you remember this, guys? It's one of the most important for solving the problems. Okay, so for example, here, which I have shown you in all these diagrams. So this was an unpolarized light here, right? So this, if this has intensity of I, the polarized light will have intensity of I by 2. Okay, whenever some unpolarized light will become polarized, the intensity will become or will be reduced by half. Cool, right? So I have to remember this. Okay. So and notice here, I'm showing it here with a diagram. There is a polarizer here, and there is an optical axis in this direction. There is an optical axis in this particular direction. An unpolarized light, see, which is red dot and blue dot perpendicular to each other, is passing through the polarizer. The polarizer will allow for the light. For example, if this is the axis and this polarizer will allow light exactly which is in this axis. Perpendicular to that direction or some different direction, it will be blocked or absorbed. Okay, it will absorb by some quantity, and only light which is exactly in the plane of this polarizing axis will pass through this. Okay, for example, if this has an intensity of I naught, this plane polarized will have an intensity of I naught by 2. This is true only for unpolarized to polarizer. Okay, should be very careful about it. If you're using a polarized light already, that will be a different case. But always remember, when unpolarized light get polarized, intensity reduces by half. Cool, right? Am I clear, guys? Come on, click on yes if I'm clear about these all these 3 points, what I've written on the board. Okay, this is the first process which you need to understand. I hope you're clear. Okay, cool, awesome. Okay, so moving ahead. Okay, so let us try to understand some problems and some basic concepts of this particular absorption polarization technique. Okay, so now instead of taking one polarizer, I have two polarizers. Okay, polarizer 1 and polarizer 2. As I already told you, polarizer is also called as analyzer. Okay, it's also called as analyzer. Okay, so now what I'm trying to do is I'm taking a unpolarized light. I'm taking unpolarized light. Okay, so when I take an unpolarized light, this polarizer will pass the electric field or light wave which are in the exactly same axis. So they're getting they are passing through this particular polarizer. They come out. Other lights are completely blocked now. Block over here, right? And imagine I'll take one more polarizer and I'll keep this polarizer in the same axis of such that of this polarized light. Okay, I got a polarized light, and this light and this polarizing axis of a second polarizer are in the same direction. It will completely pass all the light. All the lights are passing again because you can notice that they're in the same axis, right? What will happen? Okay, I'll tell you one more question. Okay, what will happen if I rotate this polarizer by 90 degree? Okay, what happen if I keep one more polarizer in this direction? Okay, now the polarizing axis is perpendicular to this polarized light wave. So what will happen if I keep a third polarizer perpendicular to that? Come on, tell me what will happen now. Try, think over it. Let me see who will answer me very quick. What will happen if I keep one more polarizer, third polarizer perpendicular to this? No? That's correct, Nikita. Good. Divya, correct. Gunashri, correct. Exactly. So what happens is this polarizer will only pass the light which is exactly passing in this particular axis, but now it's perpendicular to that. If it is perpendicular to that, no, there is no light coming out of it. So there'll be nothing coming out of it. That's correct, Rajamma Gunashri. Okay, so there is no light coming out of the polarizer. Very simple, right? So yeah, see, now what I did, I just rotated this polarizer by 90 degree. When I rotate this polarizer by 90 degree, I get no light completely. So yeah, all the light is blocked. That's correct, Madhavi. Yeah, okay. Cool, right? I hope you understand this concept. Okay, and there is one small trick, okay, which is we should always remember. Okay, yeah, okay. Let me tell you the trick after I explain this Malthus law. Okay, yeah. So there is a certain mathematical concept called Malthus law, okay, which will explain the intensity. We can calculate the intensity of light wave passing out of the polarizer if I know this Malthus law. Okay, so I'll try to give you a very small derivation. Okay, but before that, let me tell you the formula. Okay, so see, when the light wave is in particular axis and a polarizer is in different axis, both of them are not exactly parallel or perpendicular to each other. They're at different angle, not at 0 or not at 90 degree. They're in between. They're in between 0 and 90 degree. Then what will happen? Okay, so then what will happen is the intensity of the outgoing light from the polarizer is proportional to cos square theta. It is proportional to the angle. Okay, so we already know that when light wave and a polarizing axis are parallel to each other, the light will pass through it. When the light and the polarizing axis are perpendicular to each other, no light is going to pass through it, right? Therefore, I can understand by concept that acha, somehow it depends on the angle. Okay, and Malthus law is again, it was derived by a person called Malthus, and he gave this particular definition. Okay, that such that the intensity of outgoing line is proportional to the cos square theta. What is theta here? Theta is the angle between the light. Okay, you have to remember it is the light of the polarized. It's the angle between the polarized light. Okay, and polarized light between angle between polarized light and the polarizing axis. Polarizing axis. Okay, so why do we need to use this formula? Okay, so there are two things you need to remember. When you use an unpolarized light and you make it polarized, the intensity will become I naught by 2. Okay, so there is no need to remember a formula for this. You have to remember this by memory. Okay, so there's one more concept. Instead of using an unpolarized light, what if I use a polarized light? Okay, what if I use a polarized light and if I try to again polarize it? What will happen if I try to polarize the polarized light? In that case, the intensity is given as I is proportional to cos square theta. You have to use Malthus law if the intensity if you're using the input as polarized light. Yeah, I not cos square theta. Exactly, that's correct. Okay, so let me write on the formula here. You remember the proportionality symbol. After removing the proportionality symbol, you get I naught cos square theta. Okay, where I naught is the maximum intensity of the light or the input intensity. Okay, I naught is the input intensity. It is the incoming intensity. This is the outgoing intensity. And theta is the angle between the polarized light and the polarizing axis. Okay, so I'll demonstrate it. I'll demonstrate an example. Okay, yeah. So before that, let me try to derive how did I get this formula. Okay, so for example, you are going to take a polarizer. Okay, so let me draw a polarizer here. Okay, and this is a polarizing axis. Here in this particular crystal structure, the light which the light can pass through if it is passing in this direction. Okay, so let me take one more color here. Imagine if there is one light wave in this direction, this light wave will pass out of this polarizer, it will come out. Not a problem, right? Imagine if there is one more light wave in this direction. This light wave is completely blocked. A light wave will be completely blocked and you get nothing here, no light at all, right? But what will happen if I keep light in this particular direction? What happens to a light which is not at 0 degree? I mean, same, they're parallel, right? Axis and light are in same degree, they're parallel to each other, so 0 degree. Now the axis and light is perpendicular to each other, so 90 degree. But what will happen in such cases? Okay, so imagine this is electric field. Imagine this the electric field is oscillating in this particular direction. What is going to happen is very simple. Okay, you have to be very careful about it. Try to understand as much as possible. Okay, so if this is an electric field is a vector. Electric field is a vector, and this is theta. So if I resolve this electric field vector, so this side component will become E cos theta, and this side component will become E sin theta. This side component will become E sin theta. And you can notice now this component which is exactly perpendicular or sorry, which is exactly parallel to the axis, this will pass. This will move into the crystal, but this will be blocked because this is perpendicular to the axis. So this is completely blocked. So what you can try to understand is E outgoing. the E outgoing. Okay, so let me write all of them as E naught. Okay, they're initial waves, right? So the E outgoing is equal to E naught cos theta. E naught cos theta is only going outside. Okay, so I can write E is equal to E naught cos theta because this is passing the screen. This is passing the polarizer. I'll square all of this. When I square all of this, I get what you know that from the initial class, intensity is proportional to amplitude square. So what is E square? E square is nothing but amplitude of electric field. इसका intensity E square होगा I and E naught square होगा I naught and cos square theta remains as it is. Okay, and don't worry, there is no derivation for your board exam, and there is no derivation for JE also. I'm just telling you how the formula came. Okay, so what's going to happen is very simple. Only components which is parallel to the polarizing axis will pass through this. Other component which is perpendicular to the polarizing axis will be blocked. And when you square such kind of concept and discuss such kind of equation, you'll get the intensity. Okay, I'll tell you very quickly one more time if you're not understood. Imagine there's a polarizer and this is a polarizing axis. Okay, if there is one light here in this kind of situation, it will completely pass out. There is one light wave in this direction, it will be completely blocked. Okay, but what will happen if I take a light which is in this particular direction? Only cos component, if this is theta, E cos theta will pass through it, E sin theta is blocked. So therefore outgoing is equal to E naught cos theta. If I square this, I get I is equal to I naught cos square theta. So this is how we get the formula. Okay, but don't worry about the formula. Okay, you need to remember the formula and yeah, you need to understand the concept. Cool, right? So now let us try to verify this Malthus law. Okay, let us try to verify this Malthus law. So our crystal here, and this is the polarizing axis, and the polarizing. I'm sending a light in the same axis. Okay, when the angle between these two is zero, such that they're parallel to each other. When theta is equal to zero, let me put the formula. I is equal to I naught cos square zero. What is cos square zero? Cos square zero is 1. What therefore I is equal to I naught. So all the light will pass through this polarizer. Okay, now put 90 degree. Okay, now rotate this axis by 90 degree. Okay, so this is what happened, right? All the light was passing through that without any problem at theta is equal to 0 degree. Now imagine the light coming out is I naught, the light coming here is I naught. Okay, and this I naught is passing through the polarizer which is of 90 degree rotation. So I coming outside is equal to I naught which is coming inside cos square theta. What is angle between the light? So this light is like this and the angle between them is 90 degree. So I'll put cos square 90. What is cos 90? Cos 90 is 0. What is 0 square? 0. So therefore this is 0. Therefore you get, see nothing is coming out. Right. So we have a mathematical formulation now. So we can use Malthus law to understand how the intensity varies for a polarized light. Okay, but always remember, in this case, I naught should be a polarized light. Okay, so this was polarized in this direction. This was polarized in this direction. And now when I rotate by 90 degree, I get nothing. Okay, but if you keep at 60 degree, when such kind of polarized light, okay, which was at 0 degree initially, now if I keep a polarizer at 60 degree, only the cos component will pass through it. Only the cos component will pass through it. Okay, I hope you're getting the idea. Right, am I clear, guys? Yeah. So and this is a concept I was telling about polarizer. It's nothing but a chain of molecules. It's nothing but a crystal. Its orientation is such a way that whatever passing through the crystals perpendicularly will be blocked, and whatever passing through the parallel crystal will be moving inside. Okay, so notice here was the unpolarized light, and this was a polarizing axis. When polarizing axis is the same direction of electric field, that light will pass and other light are blocked. So this was perpendicular to it, so this is getting blocked. Okay, so this is not passing through the polarizer. Okay, so this was unpolarized light and this is polarized light. Cool, right? Yeah. So now let me demonstrate few problems before I give you some numericals to solve by yourself. I'll try to demonstrate few problems. Okay, which is okay. So now let me ask you a series of questions. Okay, I need all of you to answer my questions. Okay, so now I'm taking a polarizer in which polarizing axis he is here. Okay, and I'm taking an unpolarized light. Okay, I'm taking an unpolarized light. Okay, so this is the question. So guys, if the intensity is I naught, what will be the intensity of the outgoing light? Come on, answer me quick. And angle between them is 0 degree now. What will be the intensity of an unpolarized light when it is getting polarized for the first time? Let me see who will answer me quick. Okay. So this was unpolarized. This was unpolarized. Now I'm getting polarized. Gunashri, take it again. That's correct, Pallavi. Okay. So this is polarized. Yeah. Correct, Gunashri. Cool. So exactly right. YouTube guys, anyone? Anyone from YouTube? Yeah. So exactly what happens is for the first time when an unpolarized light will get polarized, the intensity will be half of the initial intensity. So if this is I naught, so the outgoing intensity, which is only in this particular axis, will be I naught. This will have the intensity, sorry, I naught by 2. It will be having exactly half the intensity of the initial incoming light wave. So the polarization intensity is half of it. Am I clear? Okay. So now what I'm going to do is I'm going to take the same light. Okay, this kind of light which is already polarized. ये तो polarized हो गया पहले से. Okay. So okay, now let me continue the question here only. Okay. So that was a bad line. Let me erase that. Yeah. So let me continue the question from here only. Okay. So now I'm taking one more polarizer. I'm taking one more polarizer. Okay. So now I'm passing this same light, which I got in the same direction. Okay. This has an intensity of I naught by 2. So this light wave has an intensity of I naught by 2. What will happen if I pass this light through this polaroid? So this is a polarized wave. So this is a polarized wave. What will happen if I pass a polarized light wave through a polarizing axis in the same direction? If both of them are in the same direction, what will be the final output intensity? Yeah. So what you have to do is for a polarized light, if your input is also always a polarized light, you have to use the Malthus law. Okay. Use I is equal to I naught cos square theta. So use Malthus law if you're using polarized light for polarizing. Okay. So outgoing light intensity is I don't know how much it is, so write it as I. That's correct, Gunashri. Okay. And so what's the incoming intensity? Incoming intensity is I naught by 2. Okay. So incoming intensity is I naught by 2. So write it as I naught by 2. What is the angle? The angle is 0 degree because both of them are parallel to each other. So it becomes cos square 0. What is cos 0? 1. What is 1 square? 1. Therefore, this intensity also will be equal to I naught by 2. See, initially at I naught, after polarizing for the first time, I get I naught by 2. Then if I again keep the polarizer in the same direction, I get I naught by 2. All the light is passing through this without any problem. Okay. And if I rotate this by 90 degree, if I rotate this by 90 degree, I'll get 0 light, as already told you, because then I is equal to I naught cos square theta. The incoming, so this is incoming light is a polarized light. So I'm going to use the Malthus law. Outgoing intensity I is equal to incoming intensity I naught by 2. What is the angle between them? 90 degree. What is cos 90 is 0. 0 square is 0. Therefore, total intensity is equal to 0. So if the polarizing axis is rotated by 90 degree, no light is coming out. No light is coming out. Right. Okay. So now I'll ask you a question. Same question. Okay. So imagine I have a polarized light. So this is a polarized light. Okay. So this polarized light has an intensity of I naught already. This is a polarized light. And I'm using crystal at 45 degree. Okay. The angle between the crystal and the polarized light is 45 degree. Okay. So now can you tell me what is the intensity of coming out? What is the outgoing intensity? Yeah. So let me see who will tell me first. What is the outgoing intensity in such a cases? The incoming intensity is I naught. What is the outgoing intensity? Yeah, again same, right? That's correct, Gunashri. So we have to use Malthus law. We have to use Malthus law because it is a polarized light. Okay, since it's a polar incoming input is a polarized light, I'll use Malthus law. I is equal to I naught cos square theta. Incoming, this is outgoing, so incoming is I naught. Okay, and angle is 45 degree. What is cos 45? Cos 45 is 1 by root 2, and the square. If I square 1 by root 2, I get 1 by 2. Therefore, I is equal to I naught by 2. Completely right. Okay, that's correct, Nikita. Okay, so now what I'm going to do is, and again for this light which is coming outside, right? The light which is coming out of this polarizer has an intensity of I naught by 2. Now I'm going to keep one more polarizer at 45 degree to this light. This light was coming in this direction, right? For this polarized, this for this light, now the axis is at 45 degree. Okay, so now the angle between this light and this polarizer is 45 degree. Can you tell me what is the light coming out of this? What is the intensity of light coming out of this polarizer? That's correct, Madhavi. Okay. Yeah, that's correct, Nikita. That's correct, Gunashri. Good, good, cool. So yeah, so what's going to happen is again very simple. So since this is also a polarized light, I have to use Malthus law, which is I is equal to I naught cos square theta. What is the I naught? Is the incoming light. Incoming light has an intensity of I naught by 2, so put I naught by 2. And what is the angle between this incoming light and the polarizer? It's 45 degrees, so put cos 45. What is cos 45? Cos 45 is 1 by root 2. 1 by root 2 square is 1 by 2. So I naught into 1 by 2. I naught by 2 into 1 by 2 hoga, and this becomes I naught by 4. By 4. Okay. See, I hope you notice an awesome thing here, okay, which is very, very important. See, this polarizer is up and down. This is up and down, okay. But this polarizer has been rotated 45 degree two times. So 45 degree two times rotate kiya to 90 degree hoga. The initial angle between the initial wave and the final polarizing axis is 90 degree. Okay. So see, whenever you keep two polarizer in this direction, when they're perpendicular to each other, if I'm passing one light here, this will pass through this polarizer, but this axis will be perpendicularly blocked by this whole crystal, and I'll get zero light. I won't get any light at all if I use only two polarizer. But if you notice, if I use one polarizer in between extra, okay, instead of making directly 90 degree, if I make it just a small rotation by 45 degree, then one more rotation by 45 degree, I'll get light outside. It's something amazing, right? Did you get my point? Okay, so what I'm trying to say is, see, if you take two polarizers, okay, and keep perpendicular them to each other, if you send some unpolarized light, okay, what will happen? So it will get polarized for the first time, and now this will be completely blocked. कुछ भी नहीं आएगा वापस. It's completely blocked. But now you take some unpolarized light, okay, you take a polarizer, ये तो polarize कर जाएगा, okay. So this light is now polarized, and instead of keeping this polarizing axis by 90 degree for the first time, keep one polarizing axis at 45 degree, okay. थोड़ा light pass हो जाएगा, okay, some light is going outside of it, and again if you rotate this by 45 degree, okay, and again some light will be passing out, and we know if this is I naught, this will be equal to I naught by 2, and this will be equal to I naught by 4 from the formula. But in this case, if this is I naught, this will be equal to 0. See, notice something very awesome thing is happening. If it is direct 90 degree, you will not get nothing, but if you do it step by step, you get some amount of light outside. Okay, and proper answer for this can be only given by quantum mechanics. Only quantum mechanics can explain this in a much more detailed way. But this is called as Bell's inequality. This is called as Bell's inequality. Okay, it's not in the syllabus, but you should, I mean, really think about it. This is so awesome, right? Direct 0 to 90 degree, no light. But if I make 0 to 90 degree by keeping one more polarizer in between, then yeah, how it is rotated, you can just take, you can rotate a polarizer. It's a solid object. It's a solid object, just like your glasses. Okay, you can rotate your glasses, right? Similarly, you can rotate the polarizer also. Okay, yeah. For example, if it is some nickel cobalt crystal, this will have some polarizing axis in this direction. If you rotate this polarizer itself, the physical rotation of the polarizer will rotate the polarizing axis. Okay, we are not rotating the axis, we are rotating the polarizer itself. जब भी rotate the polarizer, axis भी rotate हो जाएगा. Okay, yeah. So okay then. So let me give an example, and let us try to solve this example. Okay, if we finish this example, we'll go for resolution very quickly. Okay. So now, yeah. So let me read out the question very clearly. A beam of natural light falls on a system of three polaroids. So there are three polaroids in this system, which are arranged in a succession. Okay, there are three polaroids arranged one by one in an order. Okay, and such that the path axis or the polarizing axis of each polaroid is turned 60 degree with respect to the preceding one. Okay, that means if there are three polaroids, okay, there is one polaroid here, there is one polarized here, polaroid here, and there is one more polaroid here. Okay, they're telling that there are three polarizers, 1, 2, 3, and the axis of these polarizers are rotated by 60 degree with respect to each other. So if this has some polarizing axis in this direction, the angle between this axis and the second polarizing axis is 60 degree, and the angle between this polarizer and this polarizer is 60 degree. Okay, so the total angle between this and this will be 120 degree. Okay, so there are two angles of 60 degree, 60 degree of three polarizers. Okay, If the intensity initial is I naught, what will be the final intensity of the light passing through all these three Polaroids? That's the question. Okay. So let me draw them very clearly. So there are three polarizer. One polarizer here, one polarizer 60-degree with respect to the old polarizer, and one more polarizer 60-degree with respect to this another polarizer, right? So this is the arrangement what I've shown in the question, what is given in the question. Now, if one light is passing, which is an intensity of phi naught, okay, come on, quickly. What is the intensity here? We'll solve as quick as possible. Okay, what is the intensity here? So this is an unpolarized light. Okay, after passing through this polarizer, I'll get a polarized light. What will be its intensity? This was a previous JE question. Okay, by the way, this was a previous JE question. Okay, that's exactly right, Nikita. Come on, guys. Anyone else who will answer me very quick? What is the intensity of a first time unpolarized light becomes polarized? Yeah, that's correct. Okay, so I naught by 2. For the first time, when unpolarized become polarized, its intensity becomes I naught by 2. Okay, Gunesh, you have to remember this concept. Okay, yeah. Okay, so now I'm using a polarized light already, and I'm taking that polarized light and passing through an analyzer of intensity uh, of an angle at 60-degree. That's correct, Madhavi. Okay, so now what will the intensity? Come on, tell me. So this has an intensity of I, this has an intensity of I naught by 2. What will be the intensity of the polarized light which is passing in this direction? Yeah, so this was initially this was coming in this direction. Now it has rotated by 60-degree. Okay, yeah. What will be the intensity now? Okay, yeah. So what's going to happen is, so we have to use Malthus law. If you remember, this what I'm trying to use here is a polarized light. So since I'm using a polarized light already, how to use Malthus law. I is equal to I naught cos square theta. Okay, therefore, what's going to happen is the intensity which is incoming, the intensity which is coming is I naught by 2, I naught by 2, and cos square theta. Sorry there for the moment of silence. Okay, so now I've got an intensity, incoming intensity of I naught by 2, and angle rotated is 60-degree. Okay, now can you tell me what is outgoing intensity? Okay, that's correct, Nikita and Gunesh. We just use the Malthus law, we'll work it out. So if initial intensity is equal to I naught by 2 and angle is 60-degree, I'll put cos square 60. What is cos 60? Cos 60 is 1 by 2. So right, 1 by 2 how to square because there is cos square. So it becomes I naught by 2 into 1 by 2 square is 1 by 4. It becomes I naught by 8. Okay, so this was this intensity was I naught by 2. So this intensity is I naught by 8. So now can you tell me what will be the final intensity after the same light passes through one more polarizer? When the light which is an intensity of I naught by 8 pass through this polarizer, can you tell me what is the intensity? Yeah, that's correct, Gunesh. Good. Who will tell me very quick? Yep. Correct, Nikita. Good. Okay. So what happens again? See, I'm using a polarized light here for polarizing. So I have to use Malthus law, which is again I is equal to I naught cos square theta. So what is I naught? What is the incoming light? I naught by 8. And what is the angle? Cos square 60-degree. The angle between this light and this polarized axis is 60-degree. Cos 60 is 1 by 4. Cos 60 is 1 by 2. 1 by 2 squared is 1 by 4. So I naught by 8 into 1 by 4 gives me I naught 8 4 so 32. So this is the final intensity passing through the all three polarizers. Okay, I hope I'm clear, right? This is the previous J question, very simple. But if you know the Malthus law and the concept that for the first time polarization from unpolarized to polarized, it becomes half. And whenever you are using a polarized light for polarizing, you have to use Malthus law. If you know these two concepts, answer both आसान हो जाएगा. Cool, right? Yeah. So I have worked out this problem step by step. I have written all the reasons and all the values here. I've solved the problem. If you still have any doubt, you can go through this when I upload the notes. Okay, step by step. So initial intensity was I naught, where it is the average intensity when it gets transmitted for the first time is I naught by 2, unpolarized light to polarized. But now I'm using, since the polarized light into the polaroid, I have to use Malthus law. And when I do the Masslow's law for 2 steps, I'll get the final answer as I naught by 32. Cool, right? Am I clear, guys? So if this method is clear, I'll move on to next method. Okay. So as I already told you, we can polarize by 3 methods. One is by absorption of crystals or by using Polaroids. Okay. Other is by reflection and other is by scattering. I'll tell you these two if you're clear with this concept. Come on, click on yes if you're clear. If I'm clear, click on. You can text me in the chat box, guys. If I'm clear, YouTube guys. Okay. Yeah. Okay, so the next method we are going to use is polarization by reflection. Okay, so how do we get a polarization by reflection? Okay, you already know that very clearly. So whenever there is reflection, okay, imagine there's a glass slab here and a light wave is hitting this glass slab. So when it hits the glass slab, it undergoes refraction and it passes through the medium. Okay, so okay, so what we're going to do the same thing here. Okay, so this is angle of incidence I, this is angle of reflection. Angle of incidence is equal to angle of reflection, and this is angle of refraction. And you know Snell's law, and you know all this concept of reflection, refraction, right? So same thing we are going to use here. Okay, but what I'm going to do is I'm going to take an unpolarized light. Okay, I'm going to take an unpolarized light. Okay, and this unpolarized light is incident on a glass or a surface which is separating two mediums. So there is medium of refractive index n1 here, and there's a medium of refractive index n2 here. So there are two different mediums. So when an unpolarized light hits on this particular medium or this particular interface, it undergoes partial reflection, partial diffraction. Okay, so this light wave will get reflected as well as refracted. Okay, it will get reflected as well as refracted. But now what is going to happen is, okay, so this is unpolarized. This is unpolarized. So these two light wave becomes partially polarized. Thoda polarization होगा, intensity कम होगा ना, because a huge light wave is coming inside and getting incident on the surface, and some amount of light is getting reflected, some amount of light is getting refracted. दोनों का intensity थोड़ा कम हो जाएगा. So both of them are partially polarized. Both of them are partially polarized. They're not completely polarized. Okay, if you imagine if there are 10 different axes, now 5 axes is going reflected and 5 axes is getting refracted. Okay, intensity thoda kam ho gaya, and this is what's going to happen. Okay, but there was a guy called Brewster. Okay, there was a guy called Brewster, and he found a special situation. He found it a special situation which was when the angle between the reflected light ray and the refracted light ray is 90 degree. जब ये दोनों reflected and refracted is 90 degree, you'll get a completely polarized light wave. Okay, so let me show that in diagram and I'll repeat it slowly. Okay, so till now what I told you is when an unpolarized light beam, okay, is reflected from a surface, okay, it can be completely unpolarized light. Okay, when the unpolarized beam hits on this surface, you can get an unpolarized beam, or you can get a partially polarized beam, or you can get a completely polarized beam. Okay, it depends on the medium, it depends on the angle of reflection and diffraction. Okay, am I clear? When an unpolarized light is incident or reflected from a surface, then the reflected wala can have three different situations, three different criteria. So the outcoming light wave can be unpolarized, it can be partially polarized, or it can be completely polarized. Okay, so let us try to understand which are the situations. Okay, so if the angle of incidence is 0 degree or 90 degree, it will be completely unpolarized. So take for example, there's a glass slab in this particular situation. Okay, and I'm taking the light wave, and if the light wave is passing in this direction, okay, if the light wave passes exactly in this direction, polarization nothing is going to happen. There is no polarization. Or the other case, if polarization happening in this direction, the polarization will happen in this direction, then also the light wave will be completely unpolarized. The light wave will be completely unpolarized. Okay, take the other case. Like if the angle is between 0 degree, so this is the angle of this is 90 degree, and this is 0 degree, normal incidence. Okay, for the angle between 0 degree and 90 degree, some degree of polarization occurs. If the light wave is coming in from in this particular some other different angle, okay, then I'll get partially polarized reflected wave. I'll get partially polarized reflected way. Okay, there's a very special condition, okay, which is for one particular angle, the beam is completely polarized. And that particular condition is the angle between the reflected ray, okay, and the refracted ray, should be 90 degree. When both of them are perpendicular to each other, when this angle is 90 degree, then this complete light which is getting reflected will be polarized. Okay, so three simple condition, guys. It's a regular reflection and diffraction for the angle of incidence which is equal to 90 degree. For the angle of incidence which is equal to 0 degree, what's going to happen is you won't get any polarization. It will be completely unpolarized. Okay, but for some other angle between 0 and 90 degree, you can get some partial polarization. Okay, but at one particular angle called Brewster's angle, you get complete polarization, and that criteria is the angle between the reflected ray and the refracted ray should be equal to 90 degree. Okay, so I'm going to show that here. Okay, pay attention. It's a very simple formula to remember, simple law to remember. Okay, so this is a regular situation. The angle of incidence will be equal to angle of reflection, and this is angle of refraction. For all other angles, see, notice here, it is getting partially polarized. Thoda polarized ho gaya, not completely, it's partially polarized. Okay, but there is a special situation, which is when the reflected ray is perpendicular to the refracted ray. That means if the angle between them is 90 degree, then the reflected ray will be completely polarized, completely plane polarized. So notice here, okay, the incident light hits on the surface. Now it is getting partially reflected and partially refracted. And when this happens, when those two meet a criteria, when the angle of incidence is equal to when the angle of refraction is equal to angle of reflection, sorry, when the angle between the reflected ray and the refracted ray is equal to 90 degree, I get completely polarized here. I get completely polarized later. Okay, very simple. Am I clear? Click on yes, guys, if the conditions is clear. Okay, so if the condition is clear, we'll derive the Brewster's law. It's very simple. Okay, am I clear? Click on yes, Zoom guys. If you have any doubts, you can ask me in the chat box. YouTube guys, am I clear? Okay, cool then. Okay, that's great. Yeah, so what I'm going to do is very simple. I'm going to use Snell's law. Okay, yeah, and one more concept here. The angle of incidence, okay, at only particular angle of incidence I get this criteria. Okay, I'll not get always the reflected ray and refracted will not always be perpendicular to each other, but only at particular angle of incidence. Okay, only when I shine the light in particular angle, I get this 90 degree. When I get this 90 degree, then the angle of incidence is called as Brewster's angle. Okay, then the angle of incidence is called as Brewster's angle. Okay, remember that condition. And we can derive the Brewster's law in a very simple way, which is by applying Snell's law. Okay, you know Snell's law, right? What is Snell's law? N1 sine I is equal to N2 sine R. For example, if this medium is of refractive index N1 and if this medium is of refractive index N2, what's going to happen? So this is an angle of incidence angle of IB. This is an angle of incidence of angle of refraction of R. So I can write, therefore Snell's law will become N1 sine IB. N1 sine angle of incidence, that is Brewster's angle, is equal to N2 sine of angle of refraction. So this is Snell's law. This is a general formula. This is a formula for this particular situation. Okay, and I'm going to do one more small calculation. Okay, resolving power is defined as, yeah, where is here? So there's a mathematical definition called resolving power is defined as 1 by theta, or 1 by angular separation. Angular separation. So what is this angular separation? Notice when when the two light bulbs are at the same position, and when you're watching the light bulbs, they make very small angle. If you take 1 point from one light bulb and one more point at one more light bulb, they have very small angle. But when you notice that there are two different light bulbs, okay, you get a better angle. The angle between the bulbs will be more. But when you get a well resolved image, angle और ज़्यादा हो जाएगा. Theta will become much more. Okay, so this is called angular separation. This is called angular separation theta, and resolving power is inversely proportional to theta. Okay, it is inversely proportional to theta. And this theta, right? For microscope, there is some other theta. For telescope, there is some other theta. Okay, and you're going to learn the theta for microscope and telescope when you go to the ray optics chapter. In ray optics, you'll learn this. If you take the theta and put it here, you can find the resolving power of the telescope and microscope without any problem. Okay. Yeah. Okay. So I hope I'm clear here. Okay. Yeah. And so let me show you the diagrammatical representation. So this is an example for a well-resolved object. You can notice that this source S1, the first light bulb, and the second light bulbs are clearly distinguishable. I can separate both of them very clearly. So they are called well-resolved objects. Okay. Or this is also a well-resolved object. I can clearly notice that there are two different bulbs. There are two different bulbs. And this is also an example for well-resolved image. Okay, so this diagram they might ask you in the board exam. Okay, which is can represent the well resolved, unresolved, and just resolved condition using the intensity diagram. They'll ask you, and then you have to write this diagram. Okay, or if it is just resolved, okay, just a moment, at a very sharp moment, you'll notice, acha, I thought initially there was one bulb, but there are two bulbs now. Okay, the first time you notice that there are two bulbs here is called as just resolved. It's called a just resolved. And when you can't differentiate, when you can't, when all of you told, acha, this was a bike, when this was a two-wheeler, that was an unresolved condition. Now the total situation is unresolved. Now the situation is well resolved because I can see there are two bulbs. Now the situation is well resolved. I can see them very clearly. Okay, see them very very clearly. Cool, right? Yep. Oh. And this was what I'm trying to say. Okay, this is not for this chapter. This is studying the ray optics, but I'll tell you how it looks. Okay, so for example, imagine I'm using a telescope which is a diameter of d. Diameter also called as aperture. So this telescope has a diameter of d. Okay, and it's trying to resolve two stars. There are two stars very far away, and it wants to separate the two stars. And the condition which you're going to study from the ray optics chapter is this one. Okay, that the R naught, the central fringe of the star, should be at least having the diameter of 1.22 lambda f by d, where d is called this aperture distance of the telescope. Okay, and lambda is the frequency of light you're using, and f is the focal length of the lens of the telescope. Okay, don't worry about this. I'm just telling you that this kind of conditions you'll be learning in ray optics. Okay, yeah, and there is no derivation again of this formula. This chapter will again come back in ray optics, so don't worry. I'm just telling you that this kind exists. Okay, yeah. So by this, the chapter is over. Okay, so we have understood what is polarization, how do we polarize and unpolarize light, what is Brewster's angle, um, what is Malus law. We have solved few examples, right, and we have solved condition for resolution of an image. What is a resolved image? What is an unresolved image? Right? Yeah. So by this, we can say that the chapter is complete. Okay. Yep. That's all, guys, for today. So for the next class, I'll be starting modern physics. Okay, dual nature of light. Okay, so I plan to complete again in 5 to 6 more classes. We'll complete modern physics. Okay, so which day is today? Today is 15th of January. So how many classes do I have in this month? I have 8 classes. Oh, I have 9 classes. Okay. So for 9 classes, oh, there is Republic Day also. So I have 8 classes. In 8 classes, I can finish dual nature of light, and I can try to start semiconductors. Cool. Yeah. Okay, that's all. Thank you, Zoom guys. Thank you, YouTube guys, for being in the class. And that's all for today. And one more question. Okay, so have you pre-board exams completed, and when is the second pre-board exam? Is the date announced for second pre-board exam? Because most of your students are not attending the classes because of pre-board. but they're missing the class, so I was just worried about it because it will be lost for the students who are missing the class, right? Okay, then see you all later. Thank you, YouTubers. I'll be ending the stream. See you all later. Bye bye. Okay. So Zoom guys, complete the NPS, then you can leave. Okay, try to complete the NPS before you go out.